Okay, so we will start the webinar. Today we are going to cover a subject which is shell and panel design. Objectives of this webinar is just to present design capabilities which CompoSIDE provides and the difference, what it makes compared to the existing tools. We want to give you ability to judge it based on their live examples and doing it during the presentation together with you. We are going to touch this based on two examples. One will be basically a little bit more complicated shell buckling example, and then we'll design the flat panel full design iteration of the flat panel in CompoSIDE. The agenda, we'll start with why CompoSIDE. We are going to give you a quick introduction to this. We are going to introduce you to one of our modules, which are basically handling the FE capabilities and design of the shells and panels. We are going to mention the modules that we are going to use during this presentation and workflows that we are going to use. Then we are going to do the practical examples of a live demo. And then we are going to basically show you the other more advanced projects that have been done using these capabilities. Okay? At the end of the presentation, we are going to answer your questions and other concerns. Please feel free to give to send your questions at any point during the webinar. Okay, let's start with why CompoSIDE. I think the main reason we identify and we believe that there is a gap in the currently available tool sets which doesn't allow to designers to convert the design from the sketch to the end product. This is inefficient currently, and we decided that there is tools needed for that to cover. And that's why we started developing CompoSIDE for the market. There are 6 unique reasons or features that make CompoSIDE addressing this gap, and we want to briefly go through them just to give you an introduction to that. First one is collaboration and integration. The platform is a web-based platform which basically allows you to manage your entire development of the CompoSIDE project. It's one single secure web-based architecture which allows you to have all data centralized with teams collaborating and working simultaneously on the projects from different parts of the world. You can control roles and permissions to any part of the platform. Also integrating your own workflow is possible, which we are going to present you in a second. One more quite important element is that there's almost no IT resources required because it's web-based, so you don't need to really worry about installing anything or having your IT team supporting you in the background. Another element is that from the very beginning, when we started developing CompoSIDE, it was CompoSIDE design focused. It doesn't mean it doesn't support other materials. There's a full freedom of choosing whatever material or geometry you like. And but the main and primary background of this platform is Composite Design. Okay, so you're going to see it that we are handling quite complex design through advanced and composite dedicated modules. Another one is centralized data management. As I mentioned, it's web-based and all data is securely stored in cloud-based environment. So it's in one place, it's used by all people at the same time, and basically you have full control of the data. Okay? You don't store anything on your local machines. It's all stored securely on the servers. You manage and maintain your data, your material data, your project data through this centralized data management architecture. We also provide quite interesting part of the project management capabilities. It's a Wikipedia which you can build the project documentations around all the elements used in the projects. Another element is the agile workflows. It comes from IT background. We decided that the design of the composite should be really more dynamic and flexible. So all the decisions that are made at the beginning doesn't really limit your design at the end. And what we implemented allows it. You can do design at any point of the design. You can change anything in the design and it will automatically update. So it's a full dynamic and flexible design experience for all involved. Okay? The fifth element is automated documentation. It's quite important and in many cases it's quite cumbersome and time-consuming. In this case we have quite optimized and efficient module which basically allows all teams to produce documents and share documents between each other. We also implemented revision and issue control, which basically is versioning system for the documentation, and also we have ability to produce elements which are used on the further part of the design and manufacturing, which is, for instance, laminate tables in the drawings. And lastly, the sixth element, which is quite unique for Composite, is the flexible licensing. And what it means is that it's a subscription and usage-based model, which allows you to have a very low entry cost of the solution, and also it's very scalable and transparent. So basically you can start as low as with very small plan with very low initial cost, and then you can scale it up at any point when you have a big project or you want to develop something special. You can work with as many users as you like. It's not licensed per user, so you can add as many users as you like, which allows and facilitates collaboration between people using this platform. All right, that was the summary of why Composite and what elements make it special and unique, and how we address this gap. And now we are going to introduce to one of the modules that basically we are going to use to design panels today. We thought that before we jump into the live presentation, we give you a bit of an overview how it works without going into too much details of the design. So what we are going to do, we are going to present you the FE interface, and we are going to present it based on capabilities using the shell buckling example, which you can see on the screen. Design of the shell, we decided to make it as a real example. It's as a curved shell with the parameters and shell geometry like that, and we are going to show you now, starting with introduction to interface. Then we are going to show you how we iterate through the buckling design. So now I hand it over to Ola. Ola is going to go and log into our platform. And we are going to present you firstly the environment, and then we are going to use this example to show you the introduction to the shell design.
So as you can see, I'm just logging into CompoSIDE, open my usual browser.
In most cases, you don't need to install anything. You need to have a web browser and one plugin, which is basically handling 3D geometry, but other than that, it's just a start installation browser. We use Chrome, as we think it's the most advanced and most versatile browser. So as you can see, Ola has logged in.
I'm already in the correct project I wanted to show you. So let's go straight into FESpace.
So as you can see, our environment is made of modules, and now we are in the module which is called FESpace, which are handling shell designs or beam designs as well. Today we are going to concentrate on the shell design, and this is what we are doing.
Okay, so first things first, a little bit about the interface of FESpace. Two very important parts are the bottom bar, where you can have all the functionalities listed, and you can use it from here, simply opening the correct windows. And another very important part of the window is the top bar. Here, for example, you can manage your layers. So the first one is only the basic geometry, so I can see my coordinate systems. Second one are the surfaces and lines. that I'm going to use, my geometrical elements. The third layer are the structural elements, so you can see I've already created them for you. We have shells here, and I will talk about them more a little bit later. Number 4, the mesh of our structure that you can see on your screens right now. The 5th layer is the layer of results, so we will talk about it a little bit later. Okay, one more thing we need to show you is the tree, the editor tree. All created elements are basically here. So for example, the sketch I created the arc on is here. Then the arc was extruded to create this surface, and then we also extruded those 2 lines to create those sheet webs.
As you can see, we support quite versatile geometric features. So we can extrude, we can loft, we can rotate, and we can do the flat panels geometry, arbitrary geometry. So it gives you quite a good flexibility to build the basic models. Ola is going to show you probably a bit more on what's in the tree. Tree is it's another way of accessing certain functions by right-clicking on it. So you can create certain things like create properties in here. We've seen it from the bottom bar, you could do it, or you could do it from here. So it's quite easy way to find your way around working in this environment.
Yeah. What I wanted to show is the shelves I created. We've prepared the laminated materials earlier, so here is our stack of the top shell of our structure, and here is the stack of the sheet webs. Okay.
You're going to learn a little bit more how to create those in the second example. At the moment we wanted just to give you a quick intro into how the FESpace works.
Yes, so after creating the shells, the structure, we also added boundary conditions and loading. Actually, we loaded the structure with a unit displacement, as you can see here. Then we've created a load case, adding all our boundary conditions, and we calculated it.
The calculation works that you can calculate single load case or set of load case, and basically this is done on the server. And you're accessing your task, we call them tasks, which are in the tree and the main tree of the composite environment, which basically brings all the results into the editor, which Ola just shows now.
Yes. What I didn't mention, we of course enabled linear buckling analysis in our load case, so now we get the buckling results. As we can see, our BLF is 0.38, and here is our buckling deformation for the first mode, the second one, and the third one.
This is initial design. Basically, we just started with something, and let's assume that we're not happy with this buckling results for some reasons, and we wanted to do a quick iteration. So alter the top curved panel to increase the buckling mode, or see what happens if we change it. And this is quite easy to do in FESpace, and Ola is going to do it in a minute.
Yeah, I just wanted to mention the results because we're gonna talk about them a little bit later. So here you can check the strains that we get, and multiplying them by the BLF we can get the critical strains, of course. The same for
internal forces.
Okay. Since Radek mentioned that we can quickly work on our structure, I will show you what we did. We simply created a parallel rule to add some additional tapes to our structure. So you simply edit the stack, enable order applies. As you can see here, it's indicated that they are using the rule I've just shown you. Okay, if I show you the mesh, we're going to quickly see that only those elements will be using those additional tapes.
You can create local reinforcement, you can limit the extent of your plies by using simple rules. It's very, very quick to do, and iterate through your design. You're going to see on the next examples how we do it in practice.
Of course. Here we have our results for the structure with tapes. The BLF is now 0.4.
So what happens, we added tapes locally into this panel, increasing stiffness or bending stiffness of this panel, which increased the BLF or buckling load factor for this panel. This is obviously an artificial case. We don't have any targets in there, but we just wanted to show you how quickly you can adapt the structure and make the changes and review results to see where your design is. Okay.
Okay. So a quick summary now.
So basically we ran two models, two basic model which was without tapes, and the other model which was having another two tapes added to the top and the bottom of the top panel. We basically extracted BLFs, then we could calculate the critical strains, which are basically drivers for your design potentially, or critical loads or critical total loads applied to the top shell. And also we can really, really quickly extract weights and other elements from the model, which we are going to show you later in the model, in the next example. As we mentioned, what happened, we can explain the difference between buckling load factor is basically driven by the local bending stiffness of the shelf. So as you can see, it's basically the same ratios between the cube root for of the thicknesses. Okay.
Okay.
All right.
Moving on.
Okay. Now we wanted to move on to give you a bit of a insight into how to work with this module, with other modules as well. So we wanted to start with an introduction to the modules and workflows, which we are going to use on the second example. As you've seen, when we logged into the platform, we logged in and we choose the project. So this is basically the first selection that you do. You can create your own projects with different roles and permissions for different people. Then you can create the products in the project, which is basically used to handle all your design data. Then there are five elements which we are going to use today to design the panels. So the first is CMDB, which is Composite Material Database. The second one is FESpace, which we are going to use for preliminary design, and then FESpace, which we just reviewed. And then we are going to show you two other modules which are responsible for generating the bill of material and reporting. As you can see, and this is basically confirming what we have been talking earlier, is that we support agile workflow. We have downstream design, so you can design from in any module, and then you can upstream modifications, so you can go and modify any element of this design chain at any point of your design. Okay, we are going to do a live demo now of the composite plate design. It's a flat panel. Basically, this flat panel design brief is as follows. We want to design flat panel for a working pressure of 5 kilopascals and with ultimate load partial safety factor of 2.7. And we know the boundary conditions are simple supported edges, the length and width and limits on the geometry are defined as follows. And then there are design targets. We have some weight targets, cost targets for the materials, and stiffness targets in terms of frequency and the maximum deflection.
Yeah, a challenge for me.
Yes. Now Ola is going to go to platform, but before we go, that normally we start with CMDB. We've prepared it for you, so Ola is going to present basically the elements which have been prepared already. So first we have to change the project. Yeah. Because we decided to run this panel as a separate project, so Ola is going to select the project and project navigator. Yeah. Now she's going to the module which is called CMDB, and here you can see that we have a project materials already pre-prepared. So we have certain things which we've already covered. We have a material selection prepared, which allows us to handle those materials in the further stages.
Yeah. So we are ready with CMDB. We can move into Lamina space.
And what we want you to show is that you can design panels, not only going into very, very detailed FE, but you can start with preliminary design using our laminate design tool based on classical laminate theory. Basically, this panel is basically falling into strip beam approximation, so you can derive loads and you can make a first initial approximation of your design in the lamina. And then maybe if you need to change some other aspects of your design like vibration or deflection or other things which are maybe more advanced, you can go to the FESpace. And we are going to start our design with lamina space. So we decided to go for sandwich laminate, pre-preg PVC foam. We are going to orientate our reinforcement to align it with transverse shorter span of the panel, because this is where we need really the material and stiffness and strength. And we are going to basically allocate thickness to the core based on this initial shear force and the strength of the core. We decided to run with 35 millimeters core. Okay.
Okay.
What we are going to check in lamina is basically strength and local stability. This is something that in most FE packages is not done.
My Google Chrome is hiding from me. Excuse me. Okay. So I'm going into lamina. As you can see, we already have a global load defined. I'm gonna create a webinar laminate.
So what Ola means by global load is that we've already input the loads in the platform, which can be used for any laminate now created in this project. So Ola is building the laminate which we decided as an initial design. Of course, you can ask why this laminate and why such a layup. It comes from experience, but also you can play and do iterations if you want to check other laminates. But we decided to go for unidirectional 1090, a bit of a biax to provide X direction stiffness core, and we use symmetric odd option to build this laminate efficiently. Okay.
Okay. The basic info for our laminate is here.
You can read from here weight, you can weight, you can read the top skin and bottom skin parameters. Also you can check the initial cost. So you can see with our initial cost is 185 euros per square meter of such a panel.
Okay, now I'm going to add the load.
So we are going to check this laminate against the loads which are derived from first principle. We want to run cylindrical bending. This is approximation of the panel. We're using global load, which basically has been defined. So we have a working load of 5,000 around bending moment and 22 shear force. This is something that we apply now. It's the factors, so safety factors are included in the platform, defined per project or per product, whatever the manager decides. So we apply the ultimate factor. And now we are going to check this laminate against those loads.
Okay, we are good on the skins and the fiber failure here.
1.5, which is all right. Now we are going to check out of plane factors. As you can see, we are okay. We are above 1. It's 1.12 factor for the out of plane core shear. What we could check as well, and this is something that CompoSIDE Lamina module calculates, is skin wrinkling with additional safety factor, which is put on top of our ultimate factor 1.5, and this gives us also above 1 factor, which basically gives us confidence that this laminate will not experience local instability of the skin. Okay?
Okay, so we are all good.
You might ask, okay, they made it up, it's all good. You could imagine yourself iterating more, changing cores, changing thickness, changing materials for the laminates or orientation. This is quite efficient and quick.
Yeah. But since we were all good, we can move into FESpace to check our stiffness requirements of the maximum deflection and the vibration.
What we want to also show going into FESpace, we want to show you that what we've done with the preliminary design is not too bad, and is matching the more advanced FE design of the panel, where basically just calculates full FE-based problem. So we are going to look at also the strength of this panel for ultimate loads to see the comparison between what we've designed in Lamina and what we will design in FESpace.
Okay, so we are back into FESpace, the module we showed you before. And we're going to start creating the geometry. I will simply draw a line on a sketch so it's easier for me to change it if I need to. Okay, I'm going to use constraints for the line.
We're working on sketches using constraints which allows very quick change of geometry, so you can change width later or whatever you think it will be necessary in your design process. So you don't have to recreate it, you can just simply change the parameters. You can also use duplication of those models and change parameters, checking different options of your design.
Okay, now I'm going to simply extrude the line. 3000 millimeters. Okay, save. And my surface is ready. So, as I mentioned before, now we're going to create a shell using this surface and using the laminate we've created in FESpace.
Ola is bringing laminate from FESpace. The idea of shells is basically that you can collect different geometry and create one shell, apply one stack, and basically manage your stack for shell element, which is basically structural element.
Okay, now I'm gonna mesh the shell. I'm not very happy with that mesh, so we're gonna work on it a little bit.
You have ability to override your standard mesh sizes to control your mesh. Ola is doing it right now. And we are going to remesh it to see whether the mesh meets our requirements.
Yeah.
This mesh is better.
Exactly. Now I'm going to just apply the boundary conditions and the loading. So as we said, all the edges will be simply supported. So I will fix all displacements. And then I'm going to apply pressure. The first one is just our working pressure of 0.05. Working. Okay. Save, and then I'm gonna also create an ultimate.
As you can see, Ola is using the integrated partial safety factors, load partial safety factors, which are project dedicated. So you don't have to worry about this. It's all consistent. All people will use the same factors in all projects. So it's a basic quality control and reassurance.
Okay. One more thing I need to do before I can calculate. I need to prepare a load case. The first one
is
the working. And the second one will be the ultimate.
As you can see, we handle different analysis types. It's linear analysis, it's buckling analysis, vibration with pre-stress, which gives pretty good spectrum of the different options.
Okay, I'm just sending the load cases to be calculated.
As you can see, the task went into the tree and is being calculated on the server, so it's basically calculating. It's quite quick. It's around 9 seconds to calculate this problem for 2 load cases.
8 seconds even.
8 seconds, good.
Yes.
What we wanted to mention is the cost transparency. We mentioned that there are certain elements are charged in the platform. Basically, we use composite units, and at any point you can check what elements are charged and how much. So you can see that this problem for 2 load cases, it costs around 9 units out of the units which are basically available to you from subscription.
Exactly.
And we are going to show you later that at any point when you are charged, you are going to be able to check your cost, and it's very, very clearly marked with the sign of the RC units.
Okay, so we already have the results. I'm going to switch off the layers now, and as you can see, the only 5th layer is enabled. Okay, our displacement is 12.8 millimeters, so we are not meeting the design criteria right now. But let's see how we are doing on the strength, considering the FE analysis. I'm going to go to RF shell.
And again, you see that we selected one load case for which we want to calculate strength. This calculation is also incurring certain cost, but you can check it before you decide whether you want to calculate it or not. It only costs 2 units to calculate strength for this particular load case, and we are going to go for it to see whether we are matching what we've done in the preliminary design.
Okay. Yeah, looks good. We are good on the fiber failure. It's 1.5,
which matches what we did on Lamina. Now you can see that we have envelope results for all the plies and for all stack for this particular shell. We also can change the failure settings, but what we are going to do, we are going to select only core to check the out of plane shear reserve factors, and that shows us 1.17, which also matches quite well our results from Lamina, and basically allows you to check the distribution of your reserve factor across all panels. As you can see, it's not uniform. What we did in Lamina, we basically checked the middle of the panel, but in here, if you have a more complicated geometry or something which is not able to be approximated with beam strip theory, you will have a full picture of the problem.
Okay.
As you can see in here also, we can check in wrinkling. If there would be any problem with wrinkling, it would show, but at the moment it's just not showing that. It's all strains and so on.
Okay. Okay. Still, we need to work on our deformation of the panel. So what I propose we do is we will add some additional tapes. I'm going to create a rule. Okay. Okay. I'm going to add some additional plies.
So what we decided to do is to add localized plies in transversely oriented to the panel, which is under 90 degrees, and basically we are going to increase the stiffness of the panel.
Okay. Let's also add the rule.
As you can see, Ola has allocated to those 2 local plies the rule, which is basically showing the local ply. The extent of rule basically drives your ply extent, and you can do multiple rules. Maybe Ola will add another rule, which is basically limit our extent of a ply in another direction. So you can think about different rules that can be applied as basically some of different rules. We have cylindrical rules, parallel rules, which allows you to very, very efficiently define your localized plies or loads.
Okay. I'm also going to add the second rule to both the plies here.
As you can see, we have only local plies in the middle of the panel. If we look at the results, it can also be reviewed together with the results. So basically, you see that the extent of the ply covers the part of the panel which deflects the most.
Okay. I'm going to run only the working load again, but this time I'm going to switch modal analysis on. We're going to find three natural frequencies, first three natural frequencies for this panel. Okay, save. Once again, you can see what the cost will be just for this one load case to be calculated.
With vibration included. The
course.
cost is driven by the complexity of a model, so for the size of a model and the complexity of your laminates, of number of areas you have. So it's quite quite transparent and quite good to control your costs. Okay, the more complex you go, the more resources it needs. So therefore, the more units is used for that.
Okay. Let's wait for the log to calculate. Again, 8 seconds. Our lucky number today. Okay. Okay.
Okay, as you can see, our deflection dropped from 12 millimeters to 9.1. So basically, we are meeting our design target of 10 millimeters, which is correct. Now, what I would like to see, Ola, is to have a basically vibration check whether we're meeting. Okay, we have the first mode, which is 150, which is above our target, which was 100 hertz. We can also visualize this and look at different modes. The other mode is 160, so it basically shows you the vibration of this panel.
Okay. One more thing we're going to see, it's the properties of our panel. So the total mass with the plies is 20.5 kilos.
It's worth mentioning that this is a basic, very simplified weights based on the FEE model without additional things which bill of material is going to cover, which is the usage and wastage factors. We are going to cover that in the next parts of the presentation. Okay. But we are okay in terms of meeting our design.
Yeah. Okay. So we were all good in FESpace, met all the criteria. Now I'm gonna create a bill of material from our FE model. So I just need to save it first. And we will quickly move to the BOM-Gen tool. One thing worth mentioning, the BOM will be derived based on the mesh of the FE model, so make sure it's the right mesh you want a bill of material of. Okay.
Having said that, you can always manually change your areas and quantities within the BOM, so it's not limited in this case.
Again, if some units will be taken from your subscription, we always will tell you that. Okay, generate BOM. Here it is.
So BOM has been generated for this particular design. If you imagine that you went back and changed the model, add another plies or change the size, you can always update this BOM, and it basically propagates all the design changes to this document.
Exactly. Here you can see the rules on the plies were already taken into account, so the area of the tapes we've used is different. And one more very practical thing, we can export a laminate table from our bill of material.
So this is a part of our automated documentation. So at the moment we've just generated full definition of this particular panel in Excel. So it basically shows you this is the laminate table with areas and quantities and weight estimate. But also you can see that we have a total design part weight, which includes usage factors defined per projects or per part, and also unique bill of materials. So you have a list of materials and quantities which can be sent or put in the drawings or sent to the manufacturers or material manufacturers providers.
Okay. So as Radek said, if you want to manually change any quantities, you can do it. But we are happy with our bill of materials, so now we can go and create a report.
You've seen it was quite quick to create a bill of material. and now it will be even quicker to create a report from that.
Exactly. I'm simply right-clicking on the product, select Create BOM Report. Okay, name it. I will choose our external customer logo, use a template, all components with costs, and save it. Here it is.
As you can see, the report has been generated, so it features our logo, which would be your logo if it's your instance, but you can add any customized logo of your partner which you work with, or certain other elements. The report is visible in here, so you can see that there is it's automatically generated. You can regenerate this document when the data is changing. By editing it. Ola is going to also edit it to show you that there's a flexibility to add elements to the report, so you can write the content or add your content. In here we are going to
add a picture.
Picture of this particular panel in the report.
Okay.
Of course you can put whatever you like in there and just have this fully documented.
Exactly.
You can export it to HTML, which is basically link at the top, and this link can be shared with other people.
Not necessarily other CompoSIDE users, but your external customers, manufacturers, and so on.
We also have, as we mentioned, we have this revision and issue control, so you can issue certain document at some point with full traceability of the changes, of the sign-off, and this document can be then sent to the end user.
Of course, you can also generate a PDF file to have it. Okay.
We are going to generate a PDF out of this bill of material, and it will be part of our documents which we are going to share with you at the end of this webinar, and will be available on our website.
So we've completed all the steps. We've met all our design criteria.
As you can see, it was quite efficient. We've done almost 2 designs together with you in a matter of half an hour, with few iterations in each, with full traceability, full picture of the design decisions made in this platform.
It was also very cheap.
Well, we wanted to be very, very open and transparent about the cost as well. It's what it costs to design this flat panel is basically what we summarize in here. So if you think about the elements that we went through, so LaminaSpace was quite, it wasn't charged at all, and the CPU. CU units were charged because it's part of a subscription, full functionality. There are elements which have been charged in FESpace. The BOM creation have been charged, and export and generation of report have been charged. If you think about the value and the added value of the elements which are charged, it's quite staggering, the value of what is charged to what it really is. So we wanted to be quite open about that and give you a full picture of what it costed. Okay. Based on the costs and based on the examples that we give you, we can go into and show you what plans we have available and what you can do with those plans. At the moment, we have 2 plans available for handling the subscription. So basically, we have one which is called CU1000, which is dedicated to low monthly use of FESpace, with quite a lot of function covered by subscription. You can use, of course, all the features which are available in CompoSIDE, but basically your monthly allowance of units which are given as a part of a subscription will probably not cover if you are a heavy user. Okay.
One more part of our presentation, we want to show you some more complex example. Our live demo was very simple. So here there are a composite bridge design, footbridge. We did the geometry at the top and the load case that we checked, the deformation. We also did the model analysis on the bridge. And if you look through our tutorials on YouTube, you will find a video that covers the design of this bridge. A pressure vessel we did together with our client. Quite complex geometry that FESpace handled very well. We were very happy with the results. and some more examples of the structures we did.
As you can see, you can really push the boundaries with it, and it's only a matter of your imaginations and a bit of the limitations of our tools, but you can really push the design problems quite heavily and efficiently as well. So that's a part of the live demo and presentation of the FESpace shell design capabilities. We are happy to see whether there are any questions. As I can see, there's a few questions which have been given during the webinar, so maybe we'll go through some of them. One question probably at the beginning of the webinar was how do I change the geometry of the panel? To answer this question, and probably it was answered during Ola's presentation, you can use constraints, you can change the basically parameters of your operations, you can also duplicate your models and change them using the same approach. So it's quite easy and flexible to change it. Another question is quite interesting, and it's what happens if I run out of units? There's of course the question of whether you have a right plan for yourself, so basically you can change the plan for the next month, but at any point you can recharge units to cover your local peaks of your work. So basically if you run out of subscription allocated units, you can buy some additional top-up units using the price of the unit per given plan.
Okay, the question about importing CAD geometry. Yeah, you can import the XF files on a sketch, then to extrude, for example, and create shells. Or for the beam design, you can also base your section design on a imported XF file.
Mm-hmm. We are working to extend this import functionality with a step files import or an IGESTEP import. This is going to be available later in the later releases. Yeah, we are working on that. It's going to come.
Okay, there is another question if we can create holes and locally reinforce shells. And yeah, that's why went back to the previous slide. We can create holes in shells, and you can reinforce it either by extruding the edge and adding materials to the shell, or by creating a beam here.
So you can run combined models with beam elements and shell elements, which is quite a good approximation and quite often in a design stage where you're really checking the feasibility. I can pick up another questions to answer is that just TED mesh. Yeah, as you can probably notice, we're using the TED mesh. The reason for that is that we've spent quite a lot of time to make sure that basically this triangle element is meeting all the benchmarking and patch testing. It's our proprietary element, which is quite matching quite good other softwares. At the moment we are working to add quad elements, which are also our proprietary elements, which are handling the layered materials. So yeah, it's coming and it's going to be available very, very soon. But at the moment the elements that we provide are quite good match with other softwares, even with quad elements.
Yeah, exactly. Any more questions?
Okay, I think let's move on. If there's any questions, please feel free to. Okay, there's another question about assemblies. I'm not sure what you mean by that, but basically, if you have multiple parts, you can build those multiple parts together. Of course, there are certain boundary conditions that you can model. This is not. We are not going as far as designing full assemblies with contacts and so on. So you can design things which are interacting with other parts, but you need to really use your engineering judgments and simplifications to model those problems. But we tend to handle those quite nicely.
Okay, there is another question: can wind loads over surfaces be analyzed within the software? Our design live demo was very simple, so we've used just unified pressure, but it can also be added as a function. The same applies for distributed edge loads. And we also handle accelerations and angular velocities in FESpace.
You can combine the load application with rules as well, so you can limit your application of your pressure to the certain part of your panels. You can define quite complex function of your pressure to apply to the surface. So we handle quite complex loads definition in there.
Yeah.
Okay, I think we've covered most of the questions. If we missed anything, well, I can promise you that we are going to answer them and send the answer directly to the person asking questions.
We promised you at the beginning we will mention our support and training site on our website. It's really worth visiting. You can find all the recorded webinars there, a link to our YouTube channel, FAQs, and other support documents. And
knowledge base as well, where we post some of the documents that we think it's worth sharing with people.
Oh, and of course you can register for a future webinar.
Exactly. You can always check our scheduling of next webinars. So of course, there are at the moment we have 2 other webinars already scheduled. So please feel free to visit this website and join our next webinar or register for our next webinar. If you're already CompoSIDE user and you have access to the platform, there are other ways to access the support. There are the support chat, which is integrated with platform. You can at any point chat with our support team. There is technical documentation called Tech Docs, which gives you comprehensive summary of the functions and functionalities. We have a link to our dedicated support and knowledge base portal, which can be used to post questions, to find answers, to log problems and
report issues.
Exactly, report issues. So we are really reviewing it regularly. We tend to support our customers efficiently, as we know that this is really important for you. As a web-based platform, we also, it's probably worth mentioning, we are doing quite regular updates and we're developing quite a lot of things. So there are a few new things coming to our current platform, which are basically going to improve the user experience and functions that we do.
We plan to share a little sneak peek very soon.
Exactly. Okay. As a reminder, we wanted to let you know how to get started. You just go on our website and you can register for free 30 days trial. It's just a matter of a few minutes and you can have full access to full functionalities of CompoSIDE. So you can probably do the same examples as we did today with a bit of a help if needed. Please feel free to give us a call if you need. If you decide to go for commercial plans, there are 2 available off the shelf at the moment. As we mentioned, CU1000, which is dedicated to lower FE users, and CU8000, which is heavy FE used or bigger teams dedicated plan. We have also enterprise ability to get enterprise plans if needed. So please feel free to contact us if you need anything else or more, or even less from what we provide as standard plans. With this, I think we covered most of the stuff, and we are 4 minutes ahead of our scheduled time. So we want to thank you very much for joining us today for this webinar. We hope that you enjoyed and it was useful. Feel free to send us any questions to support@composide.com or contact us if you have any questions related to the product or to how to use it in your organization.
One more thing from me, I might have been quite quick with CompoSIDE and FESpace, especially I work a lot in it, but you can remind yourself how to do certain things by watching our YouTube tutorials. There is quite a lot of them, and I totally recommend watching them before you start real work with FESpace and CompoSIDE.
And lastly, as we mentioned, this webinar is going to be was recorded and is going to be available from our website as well. Thank you very much for joining. We wish you a wonderful afternoon and hope to see you at our next webinar in a few weeks' time.
Yeah.
Thanks a lot.
Thank
Bye
you.
bye.